Okay, so Professor Guo just introduced a very big picture about VOCs and ozone across multiple cities in China. So next, I will narrow down the scope to focus on atmospheric reactive organics and secondary air pollution in two typical geographic settings, that is marginal seas and estuaries. So first, I would like to have a brief introduction about reactive organics. So from the very volatile organic compounds to the extremely low volatile organic compounds. So the reactive organics contain a lot of numerous organic species spanning a wide range of volatilities. As I said, from the very low volatile to the extremely low volatility organic compounds. And from the VVOC, very volatile organic compounds, to ELVOC, generally the molar mass and oxygen to carbon ratio increase, but the volatility decrease. And it is important that the reactive organics are key precursors of secondary organic aerosol, the so-called SOA and ozone. SOA and ozone are the two typical air pollutants in many places of the world. So as you can see from this diagram, the reactive organic compounds, they have a wide range of sources, such as marine emission, plant emission, biomass burning, biofuel burning, agriculture, and fossil fuel combustion, and also the other anthropogenic sources. So then the question is why we would like to focus on estuaries and marginal seas. So it is because that marginal seas and estuaries, they are connections of terrestrial and marine systems. So due to this special geographic location, there are many special features irrespective of meteorology or emission or air circulation. For example, for meteorology, there are generally higher relative humidity and warmer weather in these geographic settings. And also due to the temperature difference between the land and water areas, then sea-land breeze can be formed. And also it is same for downdrafts and divergence. So I will introduce them later. And also the chemical profiles are also special in this area because this area receives the air pollutants from both the land areas and the water areas. So thereby interplay between the continental and marine air pollutants, and also the NOx, for example, that nitrogen oxides that are emitted by fossil fuel combustion and other combustion activities such as biomass burning. So in marginal seas and estuaries, the NOx level is generally lower. So because NOx is a very important moderator of atmospheric chemistry, so due to the relatively low level of NOx, the atmospheric chemistry in marginal seas and estuaries is also different from that in other places. All right. Now, my talk will be divided into two parts. One part is also about ozone, but different from Professor Guo's talk because he already introduced the very detailed atmospheric chemistry. But my talk about ozone will be more focusing on the atmospheric circulation and how the air pollutants are accumulated and then facilitate atmospheric chemistry. Then another part is about SOA, because as I said before, reactive organics are important precursors of tropospheric ozone and SOA. So for SOA part, I will also focus on the very detailed source and also SOA chemistry. All right, now let's focus on the first part, VOCs and ozone. A very brief background is that tropospheric ozone is a long-standing challenge globally. I think Professor Guo has already introduced it in very details, and the VOCs are critical precursors. So to study the ozone pollution in the estuary, we pick up Pearl River estuary as an important place to carry out the study, because Pearl River estuary is has long been suffering from serious photochemical pollution. That is also a reason for the higher levels of air pollution in Western Hong Kong. And then to study the photochemical pollution or ozone pollution in Pearl River estuary, we selected two observation sites on the two banks of the estuary. One on the west bank, that is Qiao Island, namely QAI here, and another side is on the east bank of the estuary at Tung Chung in Hong Kong. So we conducted a sampling campaign in autumn of 2016, and the VOC, OVOC. So OVOC is oxygenated volatile organic compounds. So VOC and OVOC, and also the trace gases such as nitrogen oxides, these important precursors of ozone, were measured offline or online. And then, for example, we have obtained about 180 VOC samples and more than 120 OVOC samples at Tung Chung, and the number of samples was a little bit lower at Qiao Island, but it was also enough for us to decipher the ozone photochemistry at these two sites. And then we observed the air quality for a long period from September 25 to November 28, about 2 months. And then finally, we got a time series of the air pollutants for not only air pollutant, but also for the meteorological conditions. And if we look at the ozone variation, maybe I need to change the cursor. And if we look at the ozone concentration, we use 100 ppb as a threshold to identify the ozone absolute days. The ozone absolute means that in 1 day, the highest hourly level of ozone exceeded 100 ppb. So we identified 16 ozone absolute days at Qiao Island on the west bank, but the ozone absolute day, the number was much less. We only observed 3 ozone absolute days at Tung Chung on the east bank, which means that generally the east bank has a lower level of ozone pollution in autumn. And then later I will introduce the mechanisms for this different level of ozone pollution. And then we also classified the sampling days into 3 patterns. The pattern 1 means that the ozone episodes were observed on both sides, not only at Tung Chung, but also at Qiao Island. And in pattern 1, generally ozone at Tung Chung was higher than that at Qiao Island. So pattern 2 means that ozone episode was only observed at Qiao Island, but not at Tung Chung. So we have 13 days of these kind of episodes. And then pattern 3 means that there was no ozone episode. So all the ozone levels comply with the air quality standard at both sites. So of course, because we focus on ozone, then of course our attention was given to pattern 1 and pattern 2 cases. So if we look at the average concentrations of air pollutants and also the average meteorological conditions in these 3 patterns, if we compare pattern 1 and pattern 2, in pattern 1, OX was higher, and the ozone was also higher at Tung Chung than Qiao Island, because the pattern 1, later I will introduce, the pattern 1 has received the air masses from the northwest of Pearl River estuary, and Tung Chung was a downwind site, so suffering from higher levels of ozone pollution. But in pattern 2, okay, in pattern 2, ozone at Tung Chung was lower than that at Qiao Island. That is a more common absolute pattern, because pattern 2, there were 13 days of ozone episode at Qiao Island. And as I said before, the wind fields were different between pattern 1 and pattern 2. Now, the panel A shows the wind field for pattern 1, As you can see, the wind blows from the northwest to southeast, and then of course Tongchong and the Western Hong Kong was on the downwind, was at in the downwind direction. So it received the air masses from the upwind directions, and also during the transport of air masses, the air was aged. So hence the higher levels of ozone at Tongchong. However, in most cases, the wind prevailed from northeast to southwest. Okay, so in this case, Xiao Island was the downwind side, but not Tongchong. So that is why Xiao Island has had higher levels of ozone in this scenario. And then to further decipher the formation mechanisms of ozone pollution in Pearl River estuary and also at these two sites, we took advantage of a chemical transport model, that is WolfChem. And of course, before we use the model, we conducted a lot of simulations to reproduce the observed meteorology and also the observed air pollutants. And as a kind of validation, we compared the meteorological patterns and also the levels of air pollutants between simulation and observation. As you can see from these figures for the vertical winds, and also for ozone level and for VOC level. So they were quite comparable between the observation and the simulation. And we also use different metrics to represent the model performance, such as RMSE, COE, and IOA. So I suppose most of you are not in this discipline, so I will not go into details about these metrics. So if you are interested, you can read our papers. So the overall message is that the model performed well in simulation of not only meteorology but also chemistry. So with the aid of this model, we were able to draw the map of ozone pollution and also the meteorological fields. For example, in this case, we saw the wind blow from the north to south, and also from northwest to southeast. And this case represents the simulation for pattern 1. That is the pattern with higher levels of ozone at Tongchong. But at Xiao Island, the ozone also exceeded the standard of 100 ppb. So, and this pattern represents pattern 2, higher levels of ozone at Xiao Island and a lower level at Tongchong. So in both patterns, we observed that there were downdrafts, kind of downdrafts over the Pearl River estuary. And as you can see from the simulated ozone mixing ratio, so there were not only high ozone at these two fixed stations, but also high ozone spread over the Pearl River estuary. And in some cases, it also transported to the downwind areas over South China Sea. So the question is that what caused the high level of ozone over Pearl River estuary? Because in over the water areas, there were relatively low emissions of air pollutants. So to discover the reason, we first analyzed the meteorological patterns, the air circulation. So we found that it was mainly due to the temperature difference between the land areas and the water areas. Because, okay, in daytime under the sunlight, so the land areas will be heated up, and the temperature in land areas was higher than in water areas. So the temperature difference between land and water areas facilitated the upwind, the upwards in land areas, and in the above layer of the atmosphere, the downdrafts are formed. So the downdrafts cause the accumulation of air pollutants in Pearl River estuary. And also due to the air circulation between the land and water areas, the air pollutants are transported from the surrounding cities to Pearl River estuary. Now we show an example for CO. As you can see, at 8 o'clock in the morning, CO, as expected, higher levels of CO were assimilated in the land areas on the two sides of the Pearl River estuary. So that was due to the emission of anthropogenic activities in surrounding cities. However, at 10 o'clock, due to the air circulation between land and water areas, so the CO, high levels of CO was simulated in Pearl River estuary. So these represent a kind of transport processes from the surrounding cities to Pearl River estuary to the water surface. And then in addition to the accumulation caused by the downdraft and the divergence on water surface, we also simulated the sea land breeze, because in these in marginal seas and estuaries, sea land breeze was an important factor leading to the redistribution of air pollutants. And for example, in the early afternoon, we simulated the sea breeze that brought the air pollutants laden with ozone to the coastal areas. That is also a phenomenon that caused the accumulation of air pollutants in Pearl River estuary. And another meteorological factor is boundary layer. Boundary layer is an important meteorological parameter that influences the vertical dispersion of air pollutants. So in Pearl River estuary and also in the marginal seas, the simulation told us the relatively lower levels of boundary layer in these areas. So it suppressed the vertical dispersion of air pollutants. Overall, these processes caused the transport of air pollutants from the surrounding cities to Pearl River estuary, and then followed by the accumulation of air pollutants. And then now that the air pollutants were accumulated in Pearl River estuary, so under the sunlight, under the favorable meteorological conditions, the ozone can be formed, because ozone is formed between the reactions of the precursors under sunlight. So once there was sunlight, the ozone was formed. As you can see from this simulated figure, we indeed simulated the high levels of ozone in Pearl River estuary, which coordinated in line with the observations at Tongchong and Xiao Island on both sides of the estuary. All right. So overall, we summarized this interesting phenomenon of ozone pollution in Pearl River estuary, and we proposed the Pearl River estuary as an ozone pool, and also illustrated the chemistry and the dynamics that build up ozone level in this special geographic setting. So I listed some progresses here, but as I introduced them before, so I will not repeat it here. All right. So that is about ozone pollution in Pearl River estuary. And as I mentioned a little bit in this part, so I also mentioned the marginal sea, because some marginal sea and the estuary share some very similar meteorological and also emission characteristics. So the next part of my presentation is about organic aerosol in marginal sea. That is about a study we conducted at Hotze. So I think if you are in Hong Kong, so you must be very familiar to this site. In every weekend, there are many people hiking in that area. Hotze is at the southeast tip of Hong Kong. And why we study organic aerosol? Because organic aerosol is a significant constitute of PM2.5, an important air pollutant in China and also in many other places of the world. Organic aerosol significantly undermines the efforts to further reduce PM2.5 in China, because in comparison with the other compositions of PM2.5, organic aerosol is not easy to be controlled because of the complex sources and also the complex atmospheric chemistry. All right. As I mentioned, we conducted a sampling campaign at Hotze. As you can see from this map, it's located in the southeast tip of Hong Kong, facing South China Sea. And then to measure organic aerosol, we use two state-of-the-art instruments. One is called TAG. The full name is thermal desorption aerosol gas chromatography, time of flight mass spectrometry. And another instrument is AMS, aerosol mass spectrometry. Both these instruments can measure organic aerosol, but they have different functions. For TAG, we measure the molecular markers of organic aerosol, but for AMS, we measure the bulk concentrations. We conducted this field campaign in autumn of 2018, and later in a following up sampling campaign was conducted in autumn of 2020. So as I mentioned, we generally use tag and AMS to measure organic aerosol. Of course, we also have other instruments to provide the supporting data to us, such as the trace gas analyzer, and we measure reactive nitrogen. We measured volatile organic compounds and oxygenated VOCs, and also we use top themes to measure the gas phase oxidation products. All right, so this is the schematic of tag. So due to time limit, I will not go into details about it. I would just like to emphasize that tag can allow the measurement of organic marker every hour. It improved the measurement resolution from about 24 hours to 1 hour, and this is a big achievement because this time resolved measurement will allow us to explore the dynamic sources and also the formation mechanisms of secondary organic aerosol. And just like Professor Go talked about the QA/QC for VOC measurement, so for tag measurement, because this is a new instrument, of course, we need to make sure the data quality. So we have conducted a lot of measures to improve the measurement accuracy and the precision. And for example, we use a mix of iterated standards with comparable structures and orientation times to the target compounds to track the shift of instrument response over time. And this internal standard, in addition with the external standard, was used to quantify the concentrations of organic aerosol markers. So overall, we got a very good data set with, for example, the R-square for the calibration curve is quite high. If you are an analytical chemical person, and then you may wonder 0.8 is not a good value for R-square, but I would say for the online instrument, it is good enough. All right, and the accuracy is 1.5% to 21.2%, and precision is also good, lower than 33%, and down to 4.1%. So the method detection limit is also not high if we compare the concentrations in the of organic aerosol markers in the atmosphere. All right, and then to analyze the organic aerosol composition and also the source and formation mechanism in details, we first separate the air masses collected at this site in different groups, because as you can see from the map, this site is located in a rural area, and the local emission. So the local emission was not very intensive, but it received air masses from different directions. For example, from the coastal area, then we name it as coastal air mass. And if the continental air from inland PRD reach the site, so we name the air mass as continental air mass. And also some air mass share the origins of continental and coastal. So for this type of air mass, we name it as mixing air mass. Okay, so in this sampling campaign, continental air mass constituted about 60%. That is a majority of the air mass received at this site, and for the rest, the marine and the mixed contributed half of them, 20% and 20%. And then we first analyzed some of the concentrations of a few groups of typical organic aerosol markers. For example, the first group is isoprene SOA tracer. So it is a sum of 2-methyl erythritol and 2-methyl syretol. So the concentration is 5.1 nanogram per cubic meter. And if we look at the table, so I think it is quite straightforward to look at these two columns. Okay, if you look at the column highlighted by red, and then this is hydroxyl dicarboxylic acid, OHDCA. It had the highest concentrations 265.8 nanogram per cubic meter for the average, and then followed by levoglucosan. Okay, levoglucosan is a good tracer of biomass bonding, but for hydroxyl dicarboxylic acid, it is a secondary air pollutant with complicated formation mechanism. So later I will introduce the formation mechanism in details. And just like our observation at Qiao Island and Tongchong, we also plotted the time series of air pollutants at Hozi. And as you can see, we have black carbon, we have primary organic aerosol markers. For example, the brown one represents levoglucosan. And in the earlier phase of the sampling campaign, levoglucosan has quite a low level. However, after 7th December, then the concentration of levoglucosan jumped to a high level, and it is accounted for a great fraction of organic aerosol markers we measured. So this high level of levoglucosan in the later phase of the sampling campaign indicated the presence of biomass bonding in Hong Kong, or not necessarily in Hong Kong. It can also be transported from the upwind directions, for example, in land PRD. And then if we look at the secondary organic aerosol markers, we have listed some of them here, such as isoprene SOA tracer, monotopin SOA tracer. So both tracers were formed from the biogenic emissions, which means that the emissions from plants. Okay, and the DHOPA is an important organic aerosol tracer derived from aromaticals. So aromaticals can be emitted from vehicles, can be emitted from other combustion activities, but most of them are anthropogenic activity. And this is OHDCA. I emphasized the high concentration earlier. So if we look at the time series of OHDCA, the highest concentrations occurred in the earlier phase of the sampling campaign, especially between 1st December to 6th December. So there were high concentrations of OHDCA. And we also take advantage of the measurements of other instruments to verify our measurements. For example, for biomass bonding tracers, here we mentioned levoglucosan is a good tracer. And after 7th December, a cold front is an important meteorological pattern. A cold front brought the air masses from continental areas to the site. So, which means that the site received the polluted air masses from China mainland. And then the biomass bonding tracer increased to a higher level. And then to verify the measurement, we also made use of the other tracers measured by other instruments, such as the acetyl nitrate measured by PTR, and the MZ60, MZ73 measured by AMS. So overall, these measurements also confirmed the increase of levoglucosan level or the biomass bonding activity in the later phase of the sampling campaign after the cold front. And also we divided the air masses into 3 groups and compare the concentrations in these 3 groups. In continental air, we observed that the air was laden with mostly primary air pollutants and POA tracer. POA means the primary organic aerosol, such as CO. CO is carbon monoxide generated from the incomplete combustion activities. And then levoglucosan, as I said, that is a tracer of biomass bonding. Fatty acids and oleic acids are good markers indicating cooking activities. So in continental air, these primary air pollutants were enhanced in this type of air masses. However, in the mixed air, we observed the high level or highest level of ozone and OHDCA. I think if you remember, I emphasized many times about the high levels of OHDCA at this site, but it has different concentrations in different air masses. In coastal air, the concentration was relatively low, that is 180 nanogram per cubic meter, just about a half of the concentrations in the marine air and the mixed air. All right, and then in the marine air, we observed most abundant sulfur dioxide, which could be related to ship emissions. And also, in addition to sulfur dioxide, ozone and OHDCA was also not low in marine air. Generally, we thought the marine air should be clean, right? However, we observed high levels of some secondary air pollutants in marine air that contributed to our basic understanding, our traditional understanding. All right, and then because PEG can provide a time resolved measurement every 1 hour, we can get a data set of the organic aerosol marker. So we can draw a diurnal pattern of the organic aerosol markers for OHDCA and the monotopin SOA tracer. They exhibited higher concentrations in the day, especially in the early afternoon, consistent with the pattern of ozone and OX. So it indicated that photochemical processes or secondary formation accounted for the high levels of these air pollutants at the site. However, for isoprene SOA tracer and for levoglucosen, their diurnal pattern were quite different, just like a pattern shaped by the development of a boundary layer. Because as you can see, the low levels of these tracers are observed in daytime. Because in daytime, the boundary layer heat was the highest. So with the highest boundary layer, and then the concentration of air pollutants could be reduced. So which means that isoprene SOA tracer and levoglucosen, the diurnal pattern were mainly shaped by the development of boundary layer. And we also can have a brief review of the other diurnal patterns. For example, OX, it exhibited a peak in the afternoon, consistent with the higher levels of OHDCA and the monotopin tracer in the afternoon. And this is the development of boundary layer. As I said, the boundary layer was highest in daytime, and the temperature was also higher, which is normal. And oleic acid, this is a very interesting phenomenon. It showed a very striking peak in the evening during the time we make dinner. So which means that this can very well represent the cooking emissions. And then I mentioned the OHDCA many times in terms of the high concentration. Of course, we need to mine the data and then try to explore the formation mechanisms. And then first, we identified a good correlation between OHDCA and OX, especially in the mixed and marine air, which means that OHDCA is a secondary air pollutant, and the formation of it was facilitated by photochemical oxidation. And also, it is interesting to note that in the marine air, the highest level of OHDCA were accompanied by high levels of sulfur dioxide, so which was represented by the size of the box, the blue box. Okay. So which means that the sulfur dioxide or other air pollutants in ship emissions can facilitate the formation of OHDCA in marine air. And then, however, for monotopin SOA tracer, the phenomena were quite different. First, the correlation with OX was not very good. And also, if we look at the regression in continental air, the distribution of the data points in continental air, so it has a higher background level. Okay, the intercept just from if we look at the intercept of the regression line, it indicates a higher background level. So which means that the higher level of monotopin SOA tracer in the continental air was not caused by secondary formation, but caused by the higher background values. And then we used a source apportionment model to identify the sources of organic aerosol. We identified 6 sources, including secondary sulfate, isoprene SOA, monotopin SOA, anthropogenic SOA, biomass burning organic aerosol, and secondary nitrate. So finally, we were able to extract the data and then draw the time series of the source contribution. It is interesting to note that in line with the distribution of levoglucosen, the biomass burning contribution increased sharply from 6 December to 7th December, I mentioned that is because a cold front came and it brought the polluted air masses from China mainland to Hong Kong. So within 12 hours, the biomass burning contribution increased 4 to 5 times. So that is a significant or rapid increase in biomass burning contribution. So that cannot be achieved if we do not have the time-resolved measurement of organic aerosol markers. For example, before we use the filter to collect the sample and analyze the compositions of organic aerosol in the filter. And then generally it takes the duration of 12 hours or even 24 hours to collect one filter, which means that the data resolution is 12 hours or 24 hours. And then it is impossible with that data to identify the faster changes or rapid increase or even rapid decrease of some sources contributions. And then we summarized the contribution in different types of air masses in continental air, marine air, and mixed air. Then in continental air, biomass burning contribution was the largest source of organic aerosol. As I mentioned, that is because the biomass burning plume was brought to the site by the cold front. However, in the marine air and mixed air, the compositions of source contributions were similar. Anthropogenic SOA dominated the source contributions, and the concentration of anthropogenic SOA was much higher than biogenic SOA, which highlighted the importance of human activities in contributing to formation of secondary organic aerosol in Hong Kong. Now it comes to the conclusion. I just summarize a few key messages. First is marginal seas and estuaries in South China are experiencing significantly secondary air pollution, which may be extended to other similar geographic settings. Then, formation of secondary air pollution involve complex atmospheric chemical and physical processes, and also interplays between them. However, the impacts of secondary air pollution in estuaries and marginal seas on air quality and climate still require the comprehensive evaluation. It is also an open question where it is not well understood. Okay, so that's all of my presentation.